In this video, we're going to look at oxidation-reduction reactions, which are often referred to as redox reactions. That is a type of single displacement reaction. Next, we're going to delve a little bit deeper into single displacement reactions. So remember, single displacement reactions were reactions where you had an element by itself kicking out one of the elements in a compound so that the element that was by itself is in a compound on the product side, leaving the element it kicked out by itself. So the specific reaction examples, redox reactions. So we're going to explore redox reactions in a lot more detail. So redox reactions are also referred to as oxidation reduction reactions. So we're going to define oxidation and reduction, look at oxidation numbers, and then predict products for these as well. First, we're going to look at the reactivity of redox reactions. So how do you tell if a reaction will even go forward? Because sometimes when you have two reactants put together in a redox reaction, nothing happens, no reaction. Okay, so how do you tell if a reaction will happen or not? Well, we need to look at the activity series. Now, the activity series is another chart that you'll notice is in your lab manual in one of your reference pages, same one that is shown here. So in order to tell if a reaction will move forward, if there'll be a reaction at all, is by looking at the metals involved in the reaction. And in this case, more active metals are going to replace a less active one. So what that means is the element that's by itself on the reactant side, so in this case zinc, needs to be higher on the activity series than the metal it's trying to replace. Because if it's higher on the activity series, that means it's a more active metal. So let's find zinc and the metal it's trying to replace. So in this case, it looks like it's trying to replace copper. So we'll find both of those on the activity series. Looks like copper is down towards the bottom, and we have zinc in the middle. So it looks like zinc is higher than copper, meaning it's more active and it will replace copper. So yes, this reaction will move forward. This reaction will take place. Now, I want you to notice on this activity series the equations that come after the metal names. So these equations are called oxidation reaction equations. So you can see that labeled at the top of the table, oxidation reactions. So in the case of zinc, we have neutral zinc solid forming a zinc 2+ ion and 2 electrons. So this zinc 2+ ion, that 2+ we've talked about as being a cation, as being a charge. And the charge is occurring because that zinc lost 2 electrons. So if something loses 2 negative charges, it itself is going to become positive. Now, these charges that we've discussed at length in the previous chapters are also referred to as oxidation numbers. So we're going to look at and define oxidation numbers next. So here are some general oxidation rules for the elements on the periodic table. So rule number 1, if an element, or an atom, is in its elemental form, meaning zinc by itself, or for any of the diatomics, H2, I2, O2, N2, any atom in its elemental form is going to be neutral. So if it's neutral, its oxidation number is then 0, because oxidation numbers is just another word for the charge on that specific atom or element. Now for monatomic ions, so this means one atom ion. So the word ion means it has a charge, so an atom with a charge. Its oxidation number is going to be whatever its charge is. So in the case of zinc on the previous slide, zinc had a +2 charge, so its oxidation number would be +2. Now let's look at some general rules for specific elements. So hydrogen. When a hydrogen is with a nonmetal, like we see in the case of acids it's going to have a +1 charge. So hydroiodic acid or hydrobromic acid, right? Iodine and bromine are both nonmetals, so when hydrogen is with either of those nonmetals, it forms a +1 charge, as we've seen with the acids. Now, when hydrogen's with a metal, so let's say hydrogen is with sodium. Okay, so we have sodium hydride, so NaH. In the case of hydrogen being with a metal, it's then going to have a -1 charge, which makes sense because if you look at this compound, sodium's an alkali metal, and alkali metals always have a +1 charge. So if sodium has a +1 charge, that means hydrogen is going to have to be the anion, the negative portion, so it's going to have a -1 charge. Next, let's look at oxygen. So oxygen, when it's in a compound, is going to form a -2 charge, meaning its oxidation state will then be -2. Now, to be a little more specific, rules for specific atoms, any element in group 1A, so those alkali metals, since they always form a +1 charge in a compound, their oxidation number is going to be +1. Group 2A, the alkaline earth metals, oxidation number is going to be 2 since they form a +2 charge in compounds. Hydrogen, we already discussed on the previous slide. With nonmetals, it's a +1. With metals, it's a -1, although I did include boron here as well. Oxygen, as you saw on the previous slide, we said it was -2 for its oxidation number. I do want to point out that there are exceptions for everything, and in the case of oxygen, it will not be a -2 when it's in a peroxide. It's going to be a different oxidation number. So if it's in a peroxide, we'll have to calculate that, and we'll learn how to do that in later chapters. Aluminum, oxidation number is going to be a +3. And then group 7A, which are the halogens, they're going to be a -1. Now, remember there's an exception for this one as well. So halogens so far, we've only seen them form -1. But when they are combined with oxygen, they can actually have different oxidation states. So keep that in mind. Let's try an example where we're assigning oxidation numbers for all of the elements in a given compound. So the example we have shown here is copper 2 chlorate. So the first step would be to split it into its ions. So in this case, we would be splitting it into copper 2 plus and the chlorate ion. So how do you know that it is copper 2 plus? How do you know the oxidation number, the charge on it? Well, you could do the reverse crisscross method, where you take this number 2 that's on the outside of the chlorate ion, and that becomes the charge on the copper, meaning a +2 charge. The other way is by knowing that chlorate ion has a -1 charge. And since it has a -1 charge and there are 2 of them, indicated by this subscript of 2 after the chlorate ion, that we would have a total of a -2 charge on the anion side. So a -2 charge on the anion side would mean that we need a +2 charge on the cation side, meaning a +2 charge on the copper, because this compound as a whole is neutral, so we need the charges to cancel. So that's a little review from chapter 2. So once we have split it into its ions, the copper ion itself was the easy one to figure out. Its oxidation number will just be +2. Now for the chlorate polyatomic, we want to try to figure out what the charge on the element chlorine is and what the charge on the oxygen is. So we're going to take it even a step further. So remember our rules from the previous slide. Oxygen has a -2 oxidation state, the exception being when it's in a peroxide. So in the case of the chlorate ion, oxygen is not in a peroxide, so we know that its oxidation state should be -2. So far we have 2 of the 3 elements in the compound oxidation numbers defined. Copper's oxidation number +2, oxygen's oxidation number -2. So now the hard one, the halogen, in this case chlorine. So what do we know about the halogens? Well, the halogens usually have a -1 oxidation state, but look at the exception. The exception is when it's combined with oxygen. And looking, in this case, yep, chlorine is combined with oxygen in this chlorate polyatomic. So that means it will not have a -1 oxidation state. So we need to calculate or figure out what the oxidation state of chlorine is in this case. So how do we do that? We do that by using what we know. So here's the polyatomic ClO3 with a -1 charge. So based off of this formula, it looks like we have 1 chlorine and 3 oxygens present. So when we add the charges of the chlorine and the 3 oxygens, our total charge is going to be -1 due to that -1 charge on the polyatomic. So now we can insert what we know about oxygen. We just said oxygen, in this case, has an oxidation state of -2. So if we take the 3 oxygens that are present multiplied by -2, which is the charge on each of those oxygens, that gives us -6. We then rearrange to solve for chlorine. So we take that -1 and add 6 to it because we're taking the 6 from this side of the equation and bringing it over. So that's why it changes from a negative to a positive. And that gives us the oxidation state of chlorine, which is +5 in this case. And you can even double check your work by inserting the 5 into this equation and making sure that it equals -1. In this case, it does. +5 plus a -6 gives me -1. So we did the problem correctly. So let's bring it all together with all my messy drawings here. So in this case, the oxidation states of all the elements present, we have copper oxidation state being +2, oxygen's oxidation state being -2, and then chlorine, the one we just figured out, being a +5. Here are some examples to try on your own. Feel free to pause the video and try to work them out on your own, and I will go over the solutions now. So the question is asking the oxidation number of all the elements in the following ions or compounds. So remember, the compounds that do not have a charge by them means that they are neutral. So let's look at the first one. In this case, we have aluminum oxide. Well, the nice thing about this one is we already know the rules for these. Oxygen, when it's not in a peroxide, is going to be a -2. Aluminum, according to the chart we looked at earlier, is going to be a +3. So no calculations for that one. You can also do the calculations to check your work and make sure that your answers are correct and that it adds up to a neutral compound. So that is what is done here. Next, looking at PO3 with a -1. So in this case, there is a -1 charge. So let's look at the oxygen first. Oxygen, we know what it is. It's going to be -2 unless it's a peroxide. So we use that knowledge, knowing that it's a -2, to figure out what the phosphorus will be. Now in this case, when we set the equation, we're going to set it equal to -1 because there is a charge on this compound because it is a polyatomic. So the answers that we get when we do the calculations, as you can see off to the right, we have oxygen as the -2, and we use that to figure out that phosphorus will be a +5. Next one is H2SO4. So looking at this, I know it's an acid and the hydrogen is first. So when the hydrogen is with other nonmetals, it forms a +1 oxidation state. So we know that hydrogen is going to be a +1. Now the SO4 portion, that is a polyatomic. So the entire SO4 polyatomic has a total of a -2 charge. So oxygen itself, I'm going to write that color one in green, since it's not in a peroxide, has a -2. So we use this knowledge to figure out what sulfur is going to be. So there are 4 oxygen atoms, each with a -2 charge, added to whatever the oxidation state of the one sulfur atom is, will equal -2, the overall charge on the polyatomic. So looking at the equations off to the side, once you isolate sulfur by itself, we figure out that sulfur's oxidation state is +6. So now that we know how to identify oxidation numbers of elements present in compounds, let's delve further into these redox reactions. So remember the redox reactions, those single displacement reactions that we were looking at, that is a shortened term for oxidation and reduction reactions. So in an oxidation and reduction reaction, there's always a transfer of electrons. One species is going to lose electrons and become more positive. And I know this is counterintuitive. If you lose electrons, you become positive, okay? Because usually losing is associated with negative. But remember, since electrons are negatively charged, if you're losing a negative, you yourself are going to become positive. So losing electrons to become more positive is the oxidation side of things. The other species then is going to gain the electrons that were lost, becoming more negative because it's gaining negative charges, and that species is referred to as being reduced. Some mnemonic devices to help you remember. One mnemonic device is Leo the lion says grr. So Leo standing for losing electrons means oxidation. Gaining electrons means reduction. The other mnemonic device that's often used is oil rig. So oxidation is losing electrons. Reduction is gaining electrons. So I like to use this chart off to the right to explain oxidation and reduction. Because remember, oxidation is losing electrons. So when you lose electrons, since electrons are negative, you're actually moving up in the number line, becoming more positive. Okay, so you're losing negatively charged electrons, becoming more positive. Reduction is gaining negatively charged electrons, becoming more negative. So given a reaction scheme, how do you determine which species is being reduced and which species is being oxidized? Well, the first step is to write oxidation numbers for all the elements and ions and see what changes. Okay, so if I'm going through this example here, looking at the copper sulfate. So copper, I don't know the charge on that because that's a transition metal, but I can figure it out based off of what it is attached to. So it's attached to the sulfate ion. The sulfate ion has a -2 charge. Since there's only one sulfate ion, I know that the copper is going to have to be a +2 to balance out that -2 charge on the sulfate. So now I have the oxidation numbers written down for sulfate and for the copper. Moving on to the other reactant, zinc. So in this case, zinc is not in a compound. So that means it's an atom in its elemental form. And remember, when we have atoms in their elemental forms, they're neutral. So I'm going to put a little 0 by it to indicate that its oxidation state is 0. Moving to the products, looks like we have copper by itself as one of the products. So since copper's in its elemental form in a product, its oxidation state is 0. Now moving to the compound, zinc sulfate, since zinc is now in a compound, it's no longer neutral. It's now going to have a +2 charge. And I know that it's going to have a +2 charge because it's attached to sulfate, and sulfate, as we saw on the reactant side, has a -2 charge. So the purpose or the reason for writing down all the oxidation numbers is you want to look and see which ones changed. Okay, so first off, I'm going to cross out the one that didn't change, and that's the sulfate. Notice sulfate has a -2 charge on both sides, so sulfate was not reduced or oxidized. Looking at the other two species, copper goes from a +2 to a 0. Okay, so let's look over at our number line. So it started off at a +2, and it looks like it went down in the downward direction to get to 0. So if it went in the downward direction, that means it's reduction. Why is it reduction? Because it gained negatively charged electrons, and gaining electrons is reduction or being reduced. So in this case, it looks like copper was reduced. And with oxidation reduction reactions, they always happen in pairs. So if something is oxidized, something else needs to be reduced. Because that copper that just gained 2 negatively charged electrons, it had to gain those electrons from somewhere. So where did it gain those electrons from? Well, it gained it from the zinc, because if you look at zinc, zinc goes from neutral to a +2, meaning it started at 0 and went the upward direction to a +2. So it lost 2 electrons. It lost 2 negatives to become positive. Those 2 negatives that it lost, it gave to copper. So in the last slide, we figured out that copper went from a +2 charge to a 0 charge, meaning that it was reduced. So copper was reduced and zinc was oxidized. Now we're going to define what an oxidizing agent and a reducing agent is. So a reducing agent is the element or ion that was oxidized, or the one that loses electrons. So which one lost electrons? It was zinc, right? Because zinc went from 0 to a +2. So it had to lose 2 negatively charged electrons to become zinc 2+. So zinc was oxidized, and zinc is also then the reducing agent. So whichever one's oxidized, that's always going to be the reducing agent. Whichever one is reduced, that's always going to be the oxidizing agent. So it's kind of opposite. Why? Because the reducing agent is the agent that reduces the other substance, the species that reduces or causes the other substance to be reduced. So for the oxidizing agent in this case, we said it was copper is the one being reduced. So copper is the oxidizing agent. More specifically, the copper sulfate compound is the oxidizing agent. So let's use our knowledge of redox reactions to figure out if a reaction will occur. So the first step in figuring out if a reaction will occur is to identify what element or ion is being oxidized and what element or ion is being reduced. So in this reaction scheme here, it looks like we have aluminum reacting with iron 3 oxide to form aluminum oxide and iron. So let's identify the oxidation states for our first step. So aluminum, when it's by itself on the reactant side, in its elemental form, will have an oxidation state of 0. Looking at the iron 3 oxide compound, we know that when oxygen is not in a peroxide, it has a -2 charge. So I'm going to put -2 for the oxidation state of oxygen, and I'm also going to do that when it's in a compound with aluminum as well. So it looks like oxygen's oxidation state is not changing at all. Now let's look at iron. So when iron is in a compound on the reactant side, in this case, we're looking at iron 3. So I know that it's iron 3 because of the oxidation state on oxygen. I did the math to figure out what charge iron needed to be in order for that compound to be neutral, and it came out to be +3. Now going over to the product side, iron is by itself on the product side in its elemental form. So when it's in its elemental form, the iron on the product side is going to have an oxidation state of 0. Now the only other species we haven't written the oxidation state of is aluminum when it's in a compound. So looking at aluminum in the product side, when it's forming aluminum oxide, aluminum is going to have a +3 oxidation state. So let's figure out which species was reduced and which species was oxidized. Well, we know nothing happened to oxygen because it remained the same oxidation state on both sides. So oxygen I'm going to take out of the equation here, just so we're not focusing on that. Aluminum did change though. It went from a 0 to a +3. So since it went from a 0 to a +3, that means it lost negatively charged electrons. So losing electrons is oxidation, so that means that aluminum was oxidized. So I'm just going to write OX by aluminum, meaning that iron probably or has to be reduced because they always happen in pairs. But just to prove it, we see that it started off as a +3 and went to a 0. So in order to go from a +3 to a 0, it had to gain negatively charged electrons, and gaining electrons is reduction. So iron was reduced. So we've done the first step, identifying what's being oxidized and what is being reduced. So the next step is to find those two species on the activity series. And it looks like they don't have iron 3+, so we're using iron 2+ instead, because iron 3+ would be in the same region. So we have iron and aluminum. Once you find them on the activity series, the third step tells you how to figure out if the reaction will occur. If the element being oxidized is higher than the one being reduced, the reaction will occur. So let's see, which one's being oxidized? It's the aluminum that's being oxidized. So since aluminum's being oxidized, if aluminum is higher than iron, the reaction will occur. So will the reaction occur in this place? In this case? Yes, it will, because aluminum is being oxidized and aluminum is higher than the iron. So the reaction will occur. Here are 3 more examples for you to try. Feel free to pause and do them on your own to see if you get the correct answers. So for the steps, the first step is to find the oxidation states of all the species present. So for the first one, the oxidation states are written above. So it looks like zinc is going from +2 to a 0, so it is gaining electrons, meaning that zinc is being reduced in this case. The other species that is changing is tin. So tin is going from 0 oxidation state in its elemental form to a +2 oxidation state. So it is losing electrons. So tin is the one being oxidized. So now we find both species on the chart next to us. So tin, since tin is the one being oxidized, tin needs to be above zinc in order for the reaction to happen, because the element being oxidized needs to be higher than the ones being reduced. So tin is the one being oxidized, zinc is up here. So is tin higher than zinc? No, it is not, so that reaction will not occur. Let's look at the next one. So for the next one, we have nickel reacting with iron 2 chloride. So let's figure out what is being oxidized and what is being reduced. So looks like nickel is changing, so let's see what exactly is happening to nickel. It's going from a 0 to a +2, meaning that it is losing electrons. So if it is losing electrons, that means it is being oxidized. So let me do it in blue since I've been using blue for oxidation. Now the other species that's changing oxidation state is iron. So iron is going from a +2 to a 0, meaning it is gaining negatively charged electrons. So iron is being reduced. So then we find both of these species on the table. So nickel is the one being oxidized, so that means we need nickel to be above iron in order for the reaction to occur. So there's nickel, and where's iron? Iron's up here, so nickel is not above iron, so the reaction will not occur. Let's look at the last example. So the last example, we want to start by writing the oxidation states of all the species involved. And then figure out what is being reduced and what is being oxidized. So it looks like, start with chromium is changing. Chromium is changing from a +1 to a +2. So that means chromium is losing an electron, meaning that chromium is being oxidized. And I see there is an error on this slide. Now copper is actually being reduced because this slide is incorrect. So the oxidation state on copper on the product side is actually +1, not +2. So copper is going from a +2 on the reactant side to a +1 on the product side. So going from a +2 to a +1 means it's gaining one negatively charged electron. So if it's gaining an electron, it is being reduced. So now we find both of these on the table off to the right. The one being oxidized needs to be higher than the one being reduced in order for the reaction to happen. So where's chromium at? Chromium is right here. And then where is copper? Let's hope it's lower so this reaction can happen. And it is. Okay, so chromium is higher than copper. The one being oxidized is higher than the one being reduced. So yes, that last reaction will occur. So in class, we're going to continue on with learning how to write redox reactions and take it a step further and learn how to write their half reactions as well. So the steps to write redox reactions is, first step is you need a balanced chemical equation. Once you have the balanced chemical equation, you identify the oxidation numbers, which we've already done this a few times, right? Once you have the oxidation numbers, you identify what is reduced and oxidized. So that we're also familiar with from what we've learned from the previous slides. Once you know what is reduced and oxidized, then we'll move in to learning how to write half reactions. And this we'll cover in class along with the rest of chapter 4. So I will see you all at lecture to continue this chapter.